After getting comfortable with ROS and Gazebo, our team built an autonomous vehicle simulation. The next step in our progress was to incorporate reinforcement learning with our self-driving simulation. We started with Q-learning, an off-policy model-free RL algorithm. Although it has some limitations which will be discussed later, the simplicity of the implementation made it a great choice for our first venture into the world of RL. We expect the audience to be familiar with reinforcement learning algorithm and related R&D work. Reinforcement learning requires an agent and an environment. In our workflow, Gazebo coupled with Python's ROS API acts as the environment. Initially, we created a SDF file that describes the robot, customized the Gazebo plugin, and implemented the image processing algorithms. After the initial setup, we implemented the Q-learning algorithm in our environment and analyzed the data. In RL algorithms, the agent takes an action and receives feedback from the environment in the form of rewards. The goal of the algorithm is to find a policy that maximizes the expected value of the reward. In order to make the environment compatible with RL algorithm, we need to define our action space and observation space. We used 3 discrete action spaces: turning left, turning right, and moving forward. The observation space needs to be discrete as we are using Q-learning algorithm. We have considered 4 cases as our observation spaces. The diff-drive vehicle captures the image of the road through an RGB camera. Then the image is processed using the following steps and converted into a discrete observation state. The video shows how the diff-drive tries to reach the goal. The blue arrow is the forward vector of the vehicle and the green arrow is the direction of the goal. The goal point is calculated at the midpoint of the centroids of 2 edges. The objective of the vehicle is to minimize the angular distance between the forward vector and the goal vector. In every state, the reward function checks if the lanes are detected, and it gives rewards based on the goal. Depending on where the agent is in the environment, the Q-learning algorithm will decide the next action to be taken. Initially, the agent tries with some random actions and starts learning using the reward function. After training a few episodes, it can traverse the full path. The graph shows the convergence of Q-learning. To learn more about our work, please visit our blog linked in the description below.